All right. Hello, everyone. Welcome back to Comp 2160 Programming Practices. I hope that you all had an okay weekend. Uh, I'm getting so tired of the rain. And it's just supposed to rain more tomorrow and the day after that. Yeah. So when I go to school with my kids in the morning, we live very close to their school. And so we walk through a park, which is really I feel like I won a lottery when we bought our house and the kids got to go to the school where we get to walk through a park in the morning to get to school. But the problem now is that the city hasn't come and cut the grass for this park. And so the grass is about that tall. And in the morning, it gets really dewy. And it's also extremely puddly because the ground is saturated. And so I got to school with my kids this morning and we were all like soggy feet. You know that sound when you get squishy feet when it's raining, squish, squish, squish. Yeah, really, really uncomfortable. We got 2 weeks left in this course, and I'm pretty happy about that. I don't know about you. We've got 2 weeks left in this course, and I think we're making good progress. So the term test grading is basically done. I just want to check over it myself before I give it back to you. You should expect to get it before the end of the day today. Tomorrow is the VW deadline, so I want to make sure that you have as much information as possible to make any decision that you need to make. We're also going to be talking about assignment 3 today, and that's the last assignment for the course. So again, in terms of making sure you have all the information you need before the final VW deadline tomorrow. We're going to be taking a look at some code that's called void.c today. This code is kind of dumb. I'll say it this way. It's kind of dumb code in that the output from it doesn't really look like it's very meaningful, and it's really not very meaningful. It's more about what's happening as this code is executing. So we're going to be working with this code today in the form of I want to run it through our debugger and kind of watch how things are changing as the code is running, and then give you some idea of kind of like how we're using this new data type that we're going to talk about today. So there's only one learning outcome for today that we're taking a look at. And that is that I want you to be able to describe concepts of in-application memory management, such as first fit memory allocation, the runtime stack, and the heap and garbage collection. We're going to be looking at 2 things today. The first thing that we're going to be looking at is revisiting the heap. We have now been using the heap for a while. I want to make sure that you have a good sense of what's going on as we call malloc in terms of visualizing the heap and what it might look like. Then we're going to move on to talking about first fit memory allocation. This is called an allocation policy. We're going to be using this allocation policy in our assignment. So in terms of the way that you're being assessed on first fit memory allocation, at least initially, it's going to be on assignment 3. So, so far in C, we've got a bunch of different kinds of data types, and there's one that we haven't talked about yet, and that is called a void pointer. In C, we've got arrays. Arrays are addresses. They're not variables. We can't assign to an array in C. We can use an array as an address, but we cannot make changes to the address that it's been there. It's kind of like an address literal in C. What we found out with arrays was that we couldn't go through the process of saying, I want to return this address to a calling function because these arrays that we had were stack allocated. Then we learned about this idea of pointers. And a pointer is a variable where the value is an address. So we've got this new asterisk symbol. The asterisk symbol says that this is a pointer type. The value that's in this thing right now is an address. And if I follow this address into memory, I'm going to find a thing. I'm going to find whatever that type is. The pointer's type tells us what we'll find at that address. If we've got a character pointer, it says that if we follow that address, we're going to find characters. If we have an integer pointer, it says that we're going to follow that address and find integers. A void pointer is a variable that contains an address, but we don't have a type. We don't know what this type is. There's no real synonym for this in Java. There's no real synonym for this in Python. This is very idiomatic C and C++. A void pointer is a variable that contains an address, but it doesn't tell us what the type is if we were to follow that address into memory. We're just going to see that there's memory there, and I don't know what it is. It's a typeless address. We've been actually using void pointers as soon as we started talking about malloc. The type signature for malloc is this. It takes as input size, so this is the number of bytes that we want to allocate on the heap. And what malloc returns to us is an address. It's not saying you're going to find characters at that address, because malloc, our memory manager, doesn't know what we're going to put there. It doesn't care what we're going to put there. We want to tell ourselves what we're going to be putting into that address. Malloc itself returns an address that has that many bytes allocated, and we're free to interpret those bytes however we want. I would like to spend just a little bit of time visualizing what's going on as we're calling malloc in a C program. So I'm going to pop open my, my tablet here, and I want to start drawing some pictures. So I want to start by kind of reminding you about this whole idea of an address space for a process. So when I run my program has the ability to see an entire address space. The address space for a process system. I'm assuming that it is connected again. I'm assuming it's connected again. Maybe not. Maybe that's someone phoning to say, hey, it's got disconnected. Okay, we've got this address space for a process. This is all of main memory for our system. So this is my laptop. My laptop has 24 gigabytes of RAM installed on it. So I'm going to say that this address space ends at 24 gigabytes, and it starts up at 0. My program, when it's running, has access to all 24 gigabytes of this. Again, you take operating systems in your 3000 level courses, and you're going to find out this is a total fabrication. But for us right now, in terms of getting this idea, let's just pretend that this is what's actually happening. We've got access to this whole address space. Within the address space, then we've got a bunch of different segments in here. So there's the code segment up at the top. There's the heap segment beneath it, and then there's the stack segment at the very bottom of this thing. So we've got code, heap, and stack. The stack is what's getting modified as we call functions and return from functions. So we're pushing stack frames onto the stack. We're popping stack frames off of the stack. So this part gets modified as we call and return from functions. Stack frames get pushed. As we call, and stack frames are popped when we return. So our stack is kind of constantly changing. It's going up, it's going down as we're going through our program and calling functions. The code segment here is going to be populated. So it's going to be filled up. So it's going to be populated by our operating system. When we, us at the terminal, ask for our shell to start running this program, it's kind of like saying, hey, operating system, can you take what's in this file and then pop it right there into memory so that the instructions that are going to be executed are going to be in memory so that our processor can start working on them. And then I'm going to put a little annotation here that at some point after the stack is where our heap space starts. The heap is being modified when we call malloc and free. We're asking for the contents of our heap to be changed every time we call malloc. We're asking for the contents of our heap to be changed every time we call free. What this kind of looks like is I'm going to draw a little zoom in here. And we're going to pretend that this little zoom in here is some small parts of the heap. For the sake of illustrating this, I'm going to break this up into small parts. So this is some very small part of the overall heap structure. And what I'm going to say is that each of these locations in our tiny subpart of the heap, they all have their own address. I'm going to give it a really short address just so we can see what's on here, but the real addresses are going to be like 15 characters long of hexadecimal addresses. But we're just going to have really small ones for what we're doing right now. So I'm going to say that this is at address 0x00, 0x01, 0x02, 0x03, 0x04, 0x05, 0x06, and 0x07. So just for clarity, the notation that I'm writing here, when I write 0x, I mean that what follows is a hexadecimal number. So I don't have any letters in these addresses, but you could expect that as we go past 9, we're going to get to A, B, C, D, E, F. The way that malloc and free are kind of working here, I'm going to write a little segment of some code, some calls that we might be making to malloc and free. So I'm going to start by saying that the very first thing we're going to do is call malloc. And we're going to call malloc, and what we're passing to malloc is 5. I'm trying to allocate 5 bytes on the heap. Malloc is going to return an address. It's going to apply a policy, and it's going to find an address where there are 5 bytes that are unallocated. So we're going to say right now that malloc has the ability to see that these first 5 bytes here have not been allocated. So 1, 2, 3, 4, 5. So malloc is going to return an address to 1 here, and it's going to say that it starts here and it goes all the way to this address right here. This first chunk of 5 bytes have been allocated to that first malloc. When I call malloc again, and I'm going to say I want to allocate 3 bytes, it's going to then say, okay, I need to find 3 free bytes of space. It has some information about how to do this. It can see that this first chunk has been allocated to this. So we'll say that these next 3 bytes are the one that malloc is going to return for address 2. And it's going to occupy all 3 of those bytes. When I call free, I pass to free the address that I want to release. You can use this address again. You can use whatever's been allocated here again if you want. So if I were to say, I would like you to free whatever you allocated for address 1, then what malloc is then able to do is to kind of go through and say, all right, I don't want to do that. This whole chunk of address space is now free for reuse. This whole chunk of address space here is free for reuse. When I call malloc one last time, we're able to look at memory here and say, okay, I need 2 bytes of space. I need 2 bytes of space. These last 3 are the ones that have been allocated. These are no longer allocated by anybody anymore. And I'm going to say that malloc is applying a free space management policy. We'll look at that in a second. But arbitrarily, we're going to say that malloc is just going to return this address here. It's going to return these 2 bytes. It's going to say you can start using at address 0x02. The big difference between the heap and the stack in terms of heap allocated versus stack allocated things is that when I call functions on the stack and I've got stack allocated variables, all I have to do to say it's okay for you to reuse them is return from that function. When I return from the function, that stack frame gets popped off, and then somebody else is just going to reuse that memory. With the heap, the lifetime of these allocations goes beyond the scope of a function. So when I call malloc and I return from a function, that stays allocated for other functions to be able to use that address that has been returned to me by my standard library. It's okay for everybody? Yeah. So in this case, I'm just saying arbitrarily, I'm just going to put it there. The reality is that we're going to use, again, a free space management policy to make sane decisions about which address we're giving back. But for our example, I'm just kind of like sticking it wherever I feel like. Yeah. Yeah. Malloc can use it again. So when we call free right here, what we are telling to malloc is that I don't need this anymore. So those 5 bytes that I previously allocated, you can give them out to somebody else now because I'm not going to use them anymore. It could have started from here. Again, I'm kind of just saying, like, arbitrarily, I'm just going to stuff it down here at this spot instead. I agree. It would have made a lot more sense if me as an allocation policy would have just picked the first one. But we'll talk formally about that in a little bit. Any other questions? It's okay so far? Yeah.
Some address and number you say like the 0x00.
So that's a really good question. The question is, if I call free and then I just use that address again later, is there still going to be data in there? And my answer is that it depends on the operating system. There's this exploit type that's called use after free, which is literally what you're talking about. We're using some memory after we've called free that still has data in it. So say, for example, you've got a password tool that like stores passwords in plain text in memory, and then you call free on it, but the operating system doesn't overwrite it, it just leaves it there. Our Linux as an operating system may do something different. Windows may actually clear it. Mac OS may clear it. They may just leave it as it was before. But generally, it depends on the operating system. Yeah. That could be complicated to answer. That could be at different levels than just basic memory. Memory that we're talking about here tends to be erased when a machine gets restarted. So if you restart your phone, and it's fair for you to say a phone has an address space in the same way that my laptop does, because it literally does. But when we restart our machine, this all kind of just goes away. The file system, so when we're storing things in files, that is going to actually have similar concepts to what we're talking about here in terms of allocating things and deallocating things. When I make a new file, we have to allocate bytes on a disk. When I delete a file, we're releasing those bytes for reuse by somebody else on the disk. And so that could be part of that. That could also then be at another level of like Apple has servers that have your photos on them. And we don't really know at the junction between my phone and Apple servers what Apple does with it once I press delete on my device. So the answer to that is maybe, but it's complicated. Yeah, I hope that's an okay answer. Yeah. Okay, any other questions about this? Yeah. Yeah. So this is a good question. Thank you for asking that. So the question is, we've got malloc, and I've written this all about malloc, but there are also realloc and calloc. The main differences between malloc and calloc are that malloc says, I would like you to allocate this many bytes. That's all we're asking for. Calloc says, I want you to allocate bytes for, and I might get this backwards, so please forgive me if I'm getting this backwards because I'm not looking below, but it says, this is how big the structure is that I want to allocate. This is how many structures I want to allocate. Internally, calloc is then saying, multiply these two things together to get what size is. This is basically saying, I know that I'm going to have to call size of on something, and I want to allocate it specifically or explicitly for a bunch of objects. This is just give me bytes. That's all it's saying. Realloc, that's a fair question. So in terms of this diagram, if I were to call realloc, so I've got malloc 2 here. If I were to say on 0.5, realloc number 4, and I want to add 2 bytes to it, then what malloc is going to say is, I'm going to look here at the allocation that you've given me on position number 4. I'm going to see that you've allocated 2 bytes, and you want to add 2 bytes to it here. There isn't 2 bytes here. So I'm going to have to take all of this and copy it down here somewhere, and then give you 2 more bytes of space that you want to have allocated. So realloc is basically saying, I know that I only have 2 bytes, but I want 2 more, please. Figure it out for me. And then the implementation of realloc is figuring it out for you. Yeah.
Is it going to be the same way we implemented code? It's in called real, right? How are you going to give it like a parameter?
How are you going to give it? Sorry, can you repeat the first part of that? How are you going to give it what?
say you have so realloc, would you use realloc to call that specific situation of malloc or instance of malloc that was already created, or do you just assign it new something that say realloc is?
Realloc, how do you call it? When I call realloc, I mean, I'm going to pass it the pointer that malloc originally returned to me. And then I'm going to tell it, this is the new size that I want you to grow to. And I believe it returns something because it may need to change where that address is. So in the case that I was describing here where there's not enough space left, it might need to physically move everything around for you. So the previous pointer that you had is no longer valid because it's moved a bunch of stuff on your behalf. So I might say, you know, my pointer equals realloc my pointer, and then more bytes, please. Yeah. Okay. All right. So this is our basic structure of heap allocation. There's a big question mark here about what malloc is doing internally, and that's totally fair. We're going to look at a policy that malloc could use. I do want to look briefly at malloc source code, like what malloc is actually doing. But this is the basic idea of what our heap management code is doing internally. At this point, I want to switch and I want to start taking a look at void.c. So if you want to kind of debug along with me, bring this up on your screen, compile it with that -g flag so that we can run it with our compiler, with our debugger, and then we'll take a look at it together. So I'm going to pop back over here. I'm going to make this just a little bit smaller. Can you confirm in the backest rows if this is still big enough for you? Is that okay? Okay, thank you. So on the left of my screen here, I've got void.c. I'm going to go down to my main function in a second. But what this just declares at the top is a structure that contains data, and it has 3 properties inside of it: an integer type, a double, and an array of characters that's 128 characters long. There's 2 functions here, fill buffer, which at first glance just fills the whole thing with the letters hi over and over and over and over again. There's process buffer, which does something kind of strange, but both of them are taking as input void pointers. So they're taking as input an address, but they're not specifying what the type is at the address. Our main function here creates this character array called buffer. It allocates on the heap buffer size characters. Buffer size up at the top there is 1024. So it's 1 kilobyte of characters. We're passing that buffer to both process and fill buffer to do stuff with it. And then we're releasing the resources that we've allocated at the end of our main function. So on my right side, what I'm going to do is I'm going to recompile void here. So again, to remind you, clang wall-g. I want to make sure that I'm including debugging symbols in this. So I need to pass that -g to say, please include the source code when you compile this thing. Void.c, and I want to put my output to void. Very quickly, if I don't include the -g here and I run lldb void, if I set a breakpoint at main and I run it, I'm going to see assembly language instructions. It's not going to be what I am not capable of debugging assembly language instructions. But this is what you'll see if you forget to put -g. So if you see this, please just remember to pop that -g on. So I'm going to recompile it with -g. And I'm going to run lldb void again. I'm going to set a breakpoint on main, and I'm going to run it. So now I've got code. Now I can see what's happening here. I want to step over this first line. I think this is straightforward. This kind of looks like what we've done before. So I'm just going to hit N on this. I want to step into the fill buffer function. So buffer at this point is a type of pointer to char. The fill buffer function up at the top here takes as an input a void pointer. I will take as input an address. It doesn't matter what the type is because internally I'm going to interpret it the way that I want to interpret it. So I'm going to step into fill buffer here with S. Internally, inside of fill buffer, I am immediately casting it back to char pointer. So I'm taking as input, I have this much space at this address, but I don't have a type attached to it. Inside the function now, I'm just going to say, I'm going to treat what's at this address as a character. On the next line here, we've got max. Max is size divided by size of char. Size of char is 1. It's 1 byte for a character, so it's just size is what we're getting back here. And then I'm going to start filling by array. So what this is doing here is we've got this loop, and we're doing stir copy a bunch of times, over and over and over again. I'm going to print out what internal is right now. Internal right now is the empty string. It's just been allocated. There's nothing in it. When I do stir copy here, and I print out internal one more time, whoops. Now I've got high with the null byte attached to it. So we've got 2 characters copied plus the null byte into this buffer. On line 23 here, internal, I'm going to say p/x internal. It doesn't change the output because it's still doing what I wanted it to do. When I print this out, internal itself is an address. The value of internal is an address. The address is 5555. This is like one of those bad movie phone numbers that doesn't actually exist. 555, so on and so forth. This is the address that is contained within internal. If we follow the address, what we're finding at that address is hi null byte. If we follow it, LLDB is able to interpret it as a character because this internal variable has been declared as type char pointer. We cast buffer. So I'm going to print out buffer here. Buffer is void pointer, and it contains this address, 5555592A0. They are equal to each other, but one of them says, if you follow this address, you can interpret this as characters. The other one says, you can't interpret this as anything. It's just an address that has memory. Yeah? It's a good question. So the question is, how do I know there's a null byte? Stir copy just puts a null byte in. It does. That's one way that I know. So if we do man3 stir copy and we look at it, we can see there that it includes that terminating null byte. But I also know that because when I print out internal, it stops printing after I. We allocated this as like 1,000 characters, and it stops printing after that. And so I know that there's a null byte there because it has stopped printing after that. Yeah. So we've got this void pointer called buffer, and we've got this character pointer called internal. The value that they have is equal to each other. They're both containing the same address as their value, but here we're interpreting it as a character pointer. On line 23, we're doing some arithmetic. Internal is a character pointer, and what I am adding to this now is 2. The plus equals 2 here says, I would like to change the value of the character pointer here, internal, by adding 2 times the size of the thing that it points at. 2 times the size of the thing that it points at is still 2 because these are characters and they're 1 byte each. But this is moving my pointer to the next 2 bytes after our high. If I print out internal, and then I hit N for next, so now we've run this plus equals 2. If I print out internal again, I'm going to get that it's at 55555555559A2, which is 2 bytes after this one. Right now, our string is pointing at the null byte that we were inserting with strcopy. So buffer points back still at pbuffer. Buffer still points at the original address that was passed in. If I cast buffer to char pointer, it still has high. That was where we started copying things. And plus equals 2 now is I'm pointing at the null byte that was inserted just after that. So as I step through this, I'm going to step through it a couple times, just hitting enter here instead of pressing N to go to the next line. Right now, internal is pointing at the null byte. And if I print out char buffer, we've got high, 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 high. Every time we start this, we're overwriting the null byte with the H, and we're just kind of repeating this. And we're going to fill this whole thing up with HI, HI, HI over and over again. I'm going to skip down to process buffer. Are we OK with what's happening here? Can we predict what's going to happen in terms of what buffer gets filled with by the time we're finished? How many highs are going to be there? 512. Thank you. Yes. Did you have a question? Yeah. Yeah.
For example, we have like from our assignment like node or stack. If we were to say internal plus equals 2, would it then go by like however many bytes that normal structure was?
If that's the type of the pointer that you have, yes. Yeah. Yeah. And we're actually going to see that right away. We're going to see that we're looking at this as a structure in just a second. Yeah. OK. So now I'm going to set a breakpoint on process buffer. And the way that I'm going to do that is I'm going to quit out of the manual pages. I'm going to go back to the main function. I'm going to set a breakpoint on line 43. And then I'm going to hit C. So right now we're stuck in this loop. I don't want to sit around in this loop for an hour as it fills it up with high over and over again. So I'm going to hit C to continue. And then it will stop at my breakpoint here on line 43. So now we're back at main. And if I print out what buffer is in main, main, remember, has buffer as a character pointer. So it's going to treat it as a string. If I print out buffer, there's 512 copies of high. And then it's all terminated by a null byte at the end. I'm going to step into process buffer. Process buffer takes as input an address, this buffer. It's a void pointer. The address that's in buffer is going to be that 5555592A0. And then here on line 29, we're casting buffer to a different data type. I've accepted unaddressed as input. In order to work with it, I need to cast it to a data type to start doing things. So I'm going to hit next on this. Internal as a data type, up at the top here has those 3 fields. We've got int a, double D, char text. The max here is going to get calculated as the size of data, which is 144 bytes in total. So the number of records in this, records here, I'm using the word records to say instances of this type of structure. The number of records that are inside of this buffer that's a void pointer is going to be 1024 divided by 144 copies of that thing. I'm going to hit next. And what I want to do now is I want to print out what's at internal at position I. So internal here, remember, in process buffer, has been cast to this type data pointer. I'm going to treat this as an array here with these square braces, and I'm going to put at position I. If I print out p at I, what I get is an instance of this structure that has an integer 17684550408, a floating point number 5.83937070064322272 with an exponent of positive 199, and then high. If I print out char buffer, it's filled with high. If I print out size of int, it's 4 bytes. I'm going to print out this internal at I here again. The size of an integer here is 4 bytes. What's happening when we cast this buffer to be of type data is that whatever's inside the buffer is going to be interpreted as the internal types of that structure. This fairly big number here, in terms of being 4 bytes, is what hi is, the bits here that are hi. If we were to take the bits for this, so these are ASCII characters, they have numbers themselves, they are bits, they're interpreted as 01010101. If I were to take those bits for those 4 bytes of hi, and I turned it into an integer, I just reinterpreted it as a number, this is the number that represents hi. If I were to take the next 8 bytes, the next 8 hi, and take the bits that are in memory and interpret it as a double, it's that exceptionally large number. Text then is an array of characters that are hi, and so on, up until we get to the end of how big text is. Right now in the code, we are on line 32. We're just about to get to line 33 here. I'm going to do n, and I'm going to cause that printf to run. And what we're getting as output here is the printf. Sorry, I made this smaller so we can see it. The printf here is I'm going to print out the number I, internal at I dot a. It's that. Print out 6.2f. So this is printing out at least 6 characters on one side and then 2 decimals on the other side for this floating point number, which is that. And then I'm printing out 128 or more of those highs that we have. So this buffer goes past the end, and the null byte doesn't appear until the very end of the whole buffer. So if we were to sit here and count this, there wouldn't be 128 highs that are being printed out. It would be like the rest of the highs in the buffer, because there's no null byte there. Printf is looking for that null byte. So what I've got is I've got this code that is initializing some memory in the heap. It's filling it up with characters, and then it's reinterpreting that as a different kind of structure entirely. If you think about this for a second, malloc is allocating memory in our heap, giving us back a void pointer, and then we're doing stuff with it by turning it or casting it to a type that we're working with. And then we're using it as strings, and we're using it as nodes, and we're using it as stacks, however we want to interpret that. Any questions about this? Yeah. This part here. this part right here. This is taking buffer. So buffer here is a void pointer. This is a value. The value in this variable is just an address. I don't know what type is at it. This line is taking that pointer, that address, and it's casting it to a type of data, which is struct up at the top, a pointer to that. And so when I assign internal to this casted buffer, now I can start treating this, excuse me, as an array of data types. Yeah.
Would it be different if
So the question is, does it change anything basically if we do this? Yeah. So now we've done that, and I'm going to print out buffer. Buffer is still coincidentally the same address as it was before. If I do n and I print out internal, p internal, I think those numbers happen to be the same. I think they happen to be the same. It's kind of a coincidence that they're the same because it's still, for A, it's still hi. Yeah, and for D, it's still hi times 4. Yeah. All right. Okay. So I'm going to go back here. And what I want to do is take a look at assignment 3. Assignment 3 is available on the course webpage. We've been talking about malloc here and the heap because we are going to implement our own memory management system. We're going to be implementing an interface here that looks fairly similar to what malloc looks like, except we're going to be calling this zalloc instead of malloc. Malloc has the entire heap, and it's up to you and me as a programmer to say, I'm going to allocate this thing, and then later I will deallocate it. I'm going to call malloc, and then I'm going to call free. We're going to implement a different memory management strategy that's called zone-based memory management. Zone-based memory management is, I've got an interface that says, please allocate a zone that has this many bytes in it. And then as my program is running, I'm going to ask to allocate inside the zone. I want to have 2 bytes and 10 bytes and 15 bytes. While I'm working, I can do 2 things. I can do the same thing that I'm doing with malloc and free. I can say allocate this and then release it, allocate it and release it. Or I can say allocate, 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 and then destroy the whole thing. And don't release every individual thing that I've allocated. Yeah. Cannot spell today. Has anyone played this game before? Okay. You've seen it. In 1998, you know, in the time before time, some of us were alive, and I was 13 years old, and I loved this game a lot. Oh my God, oh no, am I really that old already? I love this game, and I forgot to bring my Game Boy today, and I feel terrible that I forgot to bring it. I have a modded Game Boy Color with like a really bright IPS color display. I'm really
Welcome to
digressing
Speedy
here,
Walkthroughs,
but
where we
I'm
show
getting
just
to
the
a
important stuff
point
to beating
here
the game.
that is,
Going Owl again.
as Link moves from screen to screen here, so as we're going to the left, to the right, up, and down, we can imagine that each
There we
of
go,
these
down
screens
here.
is a zone.
Use a bomb to blow up that thing there.
When Link enters a page, so to be
You get
clear,
the trading
Link
quest.
is,
So this guy
one right
uses the
here.
stick to hit the bees there.
And this is a fun little side quest.
get the
where you have to
honeycomb
go
from
on,
that.
like a scavenger hunt to find a bunch of stuff, and you trade with people.
Bomb that little bit there, go
As
through.
Link is going from screen to screen
You want
here,
to dash through the green crystals
we
here,
can
which
imagine
we
that
couldn't
each
do
of these
before the last
different
dungeon.
surrounding screens is a zone of memory. And as
back down
Link
through
enters
here,
the
dash into
screen,
that,
we can
push the
say
block,
that it's
get
going
the
to
chest,
allocate
50
all
rupees.
the things that we need to put onto that screen.
Make your way out
so
of
on
this
this
dungeon.
screen, there's one
Bomb the
enemy.
right wall.
On this screen,
Get a
there's a
heart
piece of a
piece.
heart. As Link
Now make
enters
your way
the
out.
screen, we can allocate that whole thing. But I don't want to have to care about releasing every individual thing that has been allocated to that screen.
Alright, we're going to head down.
So if I implemented this with memory zones, and I'm not saying this is how they did it, but if I did it, as Link leaves the screen,
And
I
we
can
get a
just
lovely shell
destroy the
there.
whole screen without having to go through and deallocate everything that I've allocated. Every time we bring up this item screen, we can say that's a different zone, and it's going to allocate all these different pieces of that thing. And as I
Right, we
press
want to
A
here,
or
you
start
can go to
again,
sleep.
I can just deallocate the entire
And that sort of brings you
zone
into this
without
dungeon
having
thing
to
here.
like
And
go
dash
through
through
and
these
figure out
guys.
which things I have allocated every single time. As long as I deallocate the zone, I should have that
Get a
whole
lovely
block
100
of
rupees
memory
from that
free
bit.
again to use for
You
something
dash to the
else.
left here and go up. We get the ocarina.
I probably
and you
could
can
sit
fall
here
back
for
down
2
and go-
hours and watch this and be like, yes, this is awesome. Yeah. Before by a lot. Ocarina of Time was on N64. Yeah. Wait, was it? Was it on GameCube or N64? Okay, thank you. Okay, good, good. I'm not like that out of touch. Obviously, this is not the same as the current, whatever the current Zelda is, but yeah, yes. Okay. Okay, yeah, okay, good, good. Thank you all for making me feel a little bit better about my age. Okay, so we're going to implement this kind of strategy. Yes, yeah. Yeah, yeah. So I want to step through this, but I'm going to show the interface that you're implementing, and maybe as part of that, we'll try to tie these two ideas together. Yes. Oh, thank you. I don't know if I should take that as a compliment or not, because now you're kind of saying you are actually quite old. So the learning outcomes for this assignment, the new learning outcomes here are, I want you to implement simple systems level solution to one of the in-application memory management techniques. The in-application memory management techniques that we're talking about here specifically are zone-based memory management and the first fit allocation policy. And the other new one is, I want you to find the build of a project by modifying an existing makefile. I've given you like 5 makefiles now. I'm going to keep giving you more makefiles. You can just take those makefiles and then modify them to work with whatever you're building for this. You don't need to make your own makefile. You are being reassessed on all of these learning outcomes. And this is everything that you were assessed on for the last assignment, for assignment 2 that you just completed. The first part here is implementing the zones interface. So I'm going to pop open the zones interface here. This is the zones interface. The very first function here that we've got is make zone. So if we're thinking about the screens on Game Boy Color, we're going to say that each of those screens just takes 128 bytes. I'm not like giving you real numbers here, but just for sake of discussion, let's say that each screen is 128 bytes. When I call this make zone, I'm going to be passing to it 128. I want to allocate 128 bytes of space for me to allocate within later. There's 2 type defs here. The first one on line 6 is Z size T. This is just a redefinition of unsigned short. All of the sizes that we're working with must be fairly small. Short, I think, is a maximum value of 16,000. If it's unsigned, it's 32,000. We're doubling that range. So everything is going to be quite small. The other thing that we're type defing here is the structure that we are going to allow our clients to work with, which is this zone type. So when I call this make zone function, we're going to create an instance of this zone structure that has within it 128 bytes or however many bytes to allocate. The zalloc function here says, I would like you to allocate this many bytes in the zone that I've been passed to you here. And just like malloc, what we're returning is a void pointer. This is an address to somewhere. We, as the people using this library, don't know or care where it is. We just know that at that address is that many bytes reserved just for me. Block size here is us being able to say, given the zone that I am working with, here's the address that was returned to me. I would like to know how many bytes are inside or how many bytes have been reserved for me for use there. So I want to ask questions about the allocation that I previously made. Zone size is how many bytes does this whole zone manage? So if I make zone with 128 bytes, I should get 128 back here. Z-free is us saying, I do want to be able to have a more traditional malloc-free relationship with this memory manager. I do want to deallocate some things sometimes. Just like free, I'm going to pass the pointer that was previously allocated to me from zalloc. And then this destroy zone is, I'm going to take the whole zone and all of its allocated memory and release it. Whether it's been freed or not, I'm going to release everything that has been allocated to this thing. The very last thing that we've got here is a function that's kind of for us to see what is the internal state of this data type that we've got. So I don't want to expose any internal details on my interface, but I will be able to print stuff out. These functions are ultimately going to give you an entire memory management system. I'm going to pop back to my web browser here. The assessment for this is going to be that you have done all of those learning outcomes. But the main thing I want to put here is that you are implementing zones.h. You do have to call malloc. Your implementation will have to call malloc. But there should be exactly 3 calls to malloc in your code. The first one is going to be when you allocate the zone object. So you're going to create your own zone structure. You have to allocate that dynamically in memory. You have to do that with malloc. The zone itself is going to have a number of bytes that it's going to manage. You have to dynamically memory allocate that. You have to use malloc to do that. You're going to be keeping track of metadata about the memory that's in the zone in a linked list. You're going to be keeping track of allocations in a linked list. You have to call malloc to allocate space for the nodes that you've created. The zalloc function or zalloc must implement this first fit allocation policy. And I'll talk about this in a little bit. You're going to be expected to test this in question 2, and then I'm going to be testing your code in question 3. As I said when we talked about static, everything that's part of the public interface is public. Anything that's not part of the public interface must now be private. You must use this static keyword on things like your invariant functions. I don't want to be able to see that from outside. And then design by contract and defensive programming when you're implementing this. I'm going to let you read this assessment on your own in terms of the rubric. But then question 2 is now you've got this zone-based memory management system. I want you to write a test harness for this. So this is Thor testing zone. This is going to be effectively the same as what you have done for assignment 2. You can take the structure that you wrote for assignment 2 and safely reuse that for this. Obviously, the tests are going to have to be different, but the harness that you've written, you should be able to just reuse that whole setup for doing this. And then in the last part, I am going to test your memory manager. This is also dating me because these books were brand new when I was a kid, and this is a Canadian reference. So sorry, but this is Franklin the Turtle. This is Franklin the Turtle. It's by a Canadian author. It's a children's book, and of course, I had all these books when I was a kid. I'm going to give you a bunch of test cases. These are not precompiled .o files this time. I will give you C files. The C files are going to use the interface that's been provided to you in zones.h. And I'm going to expect them to pass. They are going to thoroughly evaluate the behavior of your code. You can add to your own test suite if you want once you get these, but I'm not going to publish them until next Monday. So not this week, but next week. You should start working on your test of your implementation now. In terms of assessment here, the test cases that I'm going to be giving to you are each worth 4 points. I'm actually going to amend this slightly. Part points will be awarded for this. I'm going to amend this. Part points will be awarded because you're being tested on 2 things for these memory management. For these tests, you're going to be tested on correctness of output, but also on memory leaks. So I'm going to ask the graders to run Valgrind on all of my test cases with your code, and they should not leak. There should be no leaks at the end. So there'll be 2 points for each of those. I'm going to amend that, so please forgive me for changing the assignment after I posted it, but there will be part points for question 3. That's the assignment for assignment 3, and then the rest here is just kind of the same as what you've seen before. I am going to talk about this more. My goal for what we're going to start doing for the next 10 minutes and then going into tomorrow's class, at the very beginning of tomorrow's class, is to visualize what this does. What I'm going to post on the notes for today's class and then also for tomorrow's class is this file here, using zones. This is code that will use the interface for zone-based memory management, and it will invoke things like it's going to force it to do first fit in terms of allocation. We'll talk about this starting in just a second, but before I start talking about this, I did want to ask if there are any questions about the assignment. I know I'm just shouting all this at you right now, but there might be some questions you had while we were going through this. Yeah. I realize that's super tiny, so I'll just read it out loud to you. But Handin will accept submissions until Friday, June 14th at 4 p.m. and nobody is looking. So please hover your cursor over that. Do you have a question? Yeah, so the question is for the linked list, are we creating a linked list of a structure? And does each node in the linked list have a pointer to the chunk of memory that's been allocated for the zone? And the answer to that is yes. And like I said, I'm going to visualize this. I want to draw this out for you so you have a visual internal sense of what this is supposed to look like even before you get to coding. Okay.
So you mentioned in C there's no main, but there's no public or
Yeah.
but
Static makes it file private. It's not the same public private as we have with classes in Java, because those are public and private to the class versus other classes versus packages. When you get to 2150, you will see that there are even more than public, private, and protected. There's a third option, a fourth option. In C, static means file private. So it's contained within this file. There's no real enclosing scope. There's no structure that's outside of static. It's just that it's available for use only within this file. You're not allowed to link it into other files. So there isn't really a private because it's not really the same as what private means in Java. Yeah, yeah. So for evaluation, for assessment for this assignment, yes. If you have an invariant, then you must declare it as a static function because it's private to the internal implementation that you've got. I shouldn't be able to call your invariant from my main function. Any other questions? All right, okay. So I'm going to start talking about this. But in that we have 7 minutes left, I'm not really going to be able to start drawing the picture. So the picture is the first thing we're going to be doing tomorrow. Like, as we get into this room, I mean, I'll say hello and stuff, but then I'm going to start drawing this picture out. I would like to talk briefly about it, though. I want to spend some time designing this zone-based memory manager. And the way that we're going to design this is by figuring a couple things out. The first is that we're going to have some ground rules for the memory management system that we are writing in terms of how a client, so how somebody that's on the other side of our interface is going to work with this thing, and then what the memory manager needs to know to manage the memory that it has attached to it. The main ground rule here is that when we are using this zone-based memory manager, if I'm writing code that uses the zone-based memory manager, then the memory manager does all memory management for me, aside the stack. I'm not having it implement runtime stack stuff, but anytime I need to do something that would be malloc in my code, I am now going to call zalloc. Anytime I would need to free something or release the whole thing, I will call zfree and I will call destroy zone. I will not be using malloc and I will not be using free in the client library that I'm writing that uses this interface. So I will not be calling malloc in my code. The memory manager itself has to track metadata for all of the allocated memory that it has. And this metadata internally in your memory management implementation can be in the heap. So again, you're building a linked list structure. The nodes are in the heap. You will be calling malloc in your code to allocate space for your nodes in the heap. The memory manager needs to keep track of things like which memory has been allocated. So each time I call zalloc, you will be creating entries in a list that says that this is the memory that's been allocated, not necessarily to this client or this function call, but it is being used by somebody right now. Memory that's been allocated. Also keeping track of which memory the client has not allocated, and so which memory is free. You explicitly have to do this. You must keep track of which memory is allocated. You can figure out which memory is not allocated by looking at which memory is allocated and seeing what's left. You don't have to have two lists. You could implement this with two lists, but there's fewer moving parts with just one list that says this is what's allocated, and then I can compute what's left over after that. You have to keep track of, in your memory manager, what to destroy when the manager is destroyed. So as I said, you will be calling malloc exactly 3 times in your implementation. You have to keep track of the things that you have allocated. Let me rephrase that. There will be 3 mallocs in your code. You're going to call malloc every time you need to make a node. But in your source code, if I were to count malloc, I would see 3 of those instances. The way that we keep track of what is currently allocated is that our memory manager is handling memory allocation. The only way that I, as the user of this library, can allocate new memory is to ask my memory manager to allocate that for me. I'm going to call your zalloc function. I can keep track of the addresses that I have given out in this list structure that I've got attached to my implementation. Malloc does this by applying a free space management policy. This is a link to the textbook that we use in operating systems. This is something that you are free to read. You are obviously not required to read this, but everything that you know about C programming right now, you should actually be able to follow most of this. You should be able to follow most of this. This is maybe light summer reading after you finish this course. You don't have to read this, but this textbook is good. I really like this textbook. It's a good textbook. malloc and glibc use something called the best fit allocation policy. Great, thank you for this. This is a link to the source code for malloc.c. This is how it's implemented on Aviary. This is the code that gets compiled on Aviary to be your standard library. If you've got a Linux system, this is what's sitting underneath it. I'm going to go down here for a second, and I'm going to get to the point of where there's actual code. There are hundreds of lines of comments at the top. I'm going to get down to where there's actual code. I'm going to get down to where there's actual code, all the way down here where there's actual code. And I'm going to be very clear with you. glibc code is very hard to read. It's super, super hard to read. It's extremely hard to read. I don't like to read this code. I don't think it's very good code. What I do want to point at is way up here at the top. We're going to go back to the top. I'm going to scroll up instead of down. And I'm going to go up to the top. And what I want to point out here is that this memory allocation manager, malloc, uses a heuristic. So there's this word algorithm that you've seen in Comp 2080 and in Comp 1010 and in Comp 1020. An algorithm is like this list of defined steps that you must follow, and you will get a result if you follow this list of defined steps. Heuristic is, it's maybe a list of steps that you can follow, but there's also some kind of guesswork that's happening here. Malloc uses a heuristic where it tries different types of memory allocation policies. So for very big requests here, it says it uses something called the best fit allocator. We're not going to talk about best fit in this course. We're going to talk about first fit. For small, it uses something called a caching allocator. And then in between, it does its best to guess, trying to meet the both goals at the same time. Then the last point here, it relies on memory mapping facilities. That's out of scope for this course. The words best fit allocator here, when we talk about first fit, I'll also talk a little bit about best fit just so we can see it, because they are straightforward for us to see when we get to them. So I'm going to end here, and we're not quite done this. This is a half check mark now. You should now be able to describe the heap specifically. You should be able to describe this in detail, and approximately you should be able to hand wave what happens when you call malloc, which things it's doing in terms of allocating things in the heap. We're going to talk about first fit memory allocation and more about our zone-based implementation, the very first thing tomorrow in class. That's it for today.